Hello everyone, it is the advanced structure theories. Since this Thursday will be the midterm exam, so I will explain something which could be confused by you. So first, if we like to do the coordinate axis, usually we use the x and y coordinates. And for example, in the advanced structure theories, we will call the xy coordinate system as the global coordinate system. And sometimes we like to use the second coordinate system. Let's say they are the x prime and the y prime coordinate system. And in this course, usually we call the x prime and y prime coordinate system as the local coordinate system. And we will define the angle theta. Okay, so the theta will be the from the global to the local. And also okay, so remember the definition of the theta. The theta is the angle from the global coordinate system from the global x to the local x prime. And also we will define the theta if the theta rotate counterclockwise, so it will be a positive theta. Okay, so we know for the same vector, u vector, we can use the u prime I prime plus v prime j prime, or we can use the other set of the vector components. We can use the okay, so for the same vector u vector, we can use a set of the vector components u prime and v prime to express the u vector. Also, we can use another set of vector components u and v. If we use the u prime and the v prime, it means we use the local vector components, and as long as we add the prime, usually it means they are the local coordinate system. If we do not use the prime, it means they are the components for the global coordinate system. And the question is, if we got the set of the vector components, how can we get the other set of the vector components? Okay, for example, we know the u and the v. We know the vector components u and the v. How can we get the u prime and the v prime? Okay, so also remember, we can use the dot product. If we use the unit vector of the local x prime coordinate system and make the dot product with the u vector, then we can get the u prime. And so it will be the I prime dot u I plus v j. Okay, remember the uv, they are the vector components for the u vector. Okay, so the u prime will be the u times I prime dot I plus v times I prime dot j. Okay, so we can, if we can calculate the dot product between the two unit vectors, then we can get off this. And the I prime dot I will be the cosine theta, the projection of a unit vector along the x prime direction, and what will be the projected length. So it will be the cosine theta. And the I prime unit, the unit vector along the x prime make a projection to the global y direction. If this is the theta, it will be also the angle of this. So it will be the sine theta. It will be the sine theta. Okay, also we can calculate the v prime, which is the j prime dot u, and it will be u times j prime dot I plus v times j prime dot j. Okay, and this one will be the negative sine theta. This one is the cosine. Okay, so we can get the transformation vector u prime v prime equal to the cosine theta, sine theta, negative sine theta, cosine theta times uv. Okay, so remember, if the in this 2x2 matrix, if the first row, second column, or you can say the top right corner of the transformation matrix, if you use a positive sign, then this rotation matrix multiplied by the global component of a vector, then you can get the local components of the same vector. Okay, so that's the, let's say that's the R matrix times UV. Okay, so what is the R matrix? The R matrix multiplied by the global components can give you the local components. And also the R vector, the right top corner is a positive sign. Okay. Also, I think the U and the V, if we like to get the U and the V, then we can make the dot product between the U vector and the I vector. The I vector is the unit vector along the x direction. Okay, we can follow the same derivation procedure. Then we can get, which will be the cosine theta, negative sine theta, sine theta, cosine theta, times u prime, v prime. Okay. Sometimes we like to, if we got the vector components in local coordinate system, if we like to get the components in global coordinate system, then we need to multiply this matrix. And you will find for this transformation matrix, the top right corner, which is a negative sine theta. We got a negative sign here. And I will call this matrix, which is the R transpose U prime and the V prime. Okay, so remember if we multiply the R transpose to the vector components in local coordinate system, then we can get the vector components in global coordinate system. Okay, so remember what is the R matrix, what is the R transpose matrix, and which which vector components we need to multiply and which one we can get. Okay, then when we will need to transform the vector components, first, if we got the K prime matrix multiplied by the U prime matrix, which can give you the P prime. Okay, so that's the element stiffness matrix. Okay, if we got the element stiffness matrix, remember when we derive the element stiffness matrix, we like to use the local coordinate system. Since if we use the local coordinate system, then the local x prime is defined from the first nodal point to the second nodal point, and usually it is the axial direction of this element, and the y prime direction will be the the direction perpendicular to the axial direction. And for example, if we talk about the plane frame elements, the axial stiffness, which is related to the EA divided by L, and also the elongation of the elements will be the difference between the UB prime and the UA prime. If we calculate the UB prime minus UA prime, then we can get the elongation of this element. So if we use the local coordinate system, it is very clearly the x prime direction is the axial direction. We can calculate the axial stiffness. Then if we consider the y prime directions, which is the vertical displacement of this element, the vertical displacements, usually they are related to the flexural deformation and the shear deformation. Then we know when we derive the stiffness matrix related to the vertical displacement, then we need to consider the flexural deformation. The flexural deformation is also called the bending deformation. And also, sometimes we need to consider both flexural deformation and the shear deformations. Okay, so if we use the local coordinate system, which will be easier for us to derive the element stiffness matrix. So that's why usually we always derive the element stiffness matrix in local coordinate system first. Okay, so that's why I added the prime to the K, I added the prime to the U, I added the prime to the P. Okay, so that's the element stiffness matrix. After the derivation, we can get this one. If we consider the plane frame elements, the K prime will be a 6 by 6. The dimensions will be the 6 by 6. If we consider the plane truss problems, the K prime will be a 2 by 2 matrix. If we consider the space truss problems, the K prime is still 2 by 2, since the space problems, for the space truss problems, for each element, it is still a two-fourths element. For the two-fourths element, the only important deformation and the only important end force will be always along the axial direction. Okay, so that's why we like to derive the element stiffness matrix first, since we can pick out the important displacements for our considered deformations. Okay, so that's the what we get. But later we need to assemble the element stiffness matrix to the same joint, since the two end joints usually they are connected to not only one element. For the two end joints, usually there are two or three or even more elements will be connected to the same joint. But the local coordinate system is defined element by element. No matter which element we are considering, the local x prime will always be the first nodal point to the second nodal point. Okay, that's the definition for the x prime direction. But later we need to consider the contributions of the end force to the same end joint. Then the local coordinate system will be which is not the best choice if we like to consider the contributions from different elements. Okay, so at this time we like to transform the vector components from the local coordinate system to another coordinate system. Usually the chosen coordinate system will be the global coordinate system. Since the global coordinate system, there is only one global coordinate system, and we can transform no matter which element we are considering, we can transform the vector components from the local to the global, and the global coordinate system is a unique coordinate system, so it can be chosen for if we like to consider the contributions from different elements, we will choose the global coordinate system. Okay, then we like to get a k u equal to p. Okay, this is the first set of the equations we get. But later we like to calculate for the same element. For the same element, we like to get the element stiffness matrix in global coordinate system. The related nodal displacement, the u vector, the components in the u vector, they are also the components considered in the global coordinate system. And the member end force, also we like to use the global coordinate system. So that's why I didn't add the prime to all these three, the K, U, and the P, since all of them, they are in the global components. They are in the global components. Okay, so how can we derive, if we got this, how can we change it to this one? First, we know if we know the transformation matrix between the u prime and the u, also if we know the transformation matrix between the p prime and the p, then how can we get the transformation? Okay, first we know the u prime is equal to the r times U. Also, we know the U is equal to the R transpose times U prime. And the P prime is equal to the R times P. And also the P is equal to the R transpose P prime. Okay, so we know all these four relationships. The U prime is equal to R times U. The U vector, they are the vector components in global coordinate system. The U prime, they are the vector components in local coordinate system. We know the U and the U prime. Okay, we need to multiply the R transpose to the U prime, then we can get the U. Okay, so the transformation matrix we can calculate. Remember, whenever we multiply the R, we need to post multiply by the vector components in global. Then we can get the vector components in local. Okay. Reverse. We need to multiply the R transpose to the U prime to get the U. Then how can we move from this point to this point? First, we need to multiply the K prime by the U prime, which is the P prime. P prime is equal to the K prime multiply the U prime. Okay, so that's the relationship we got so far. If we like to move this to this one, first we can change it to the K prime, to the R, to the U. Okay, so first we can change the U prime by the R times U. Okay, so the post multiply vector, which is the target we like to get, the K in global coordinate system must be multiplied by the U. Okay, so K prime times R post multiplied by the U can give you the P prime, But in these expressions, we like to get the P vector. The P vector, they are the force vector, the member end force vector in global components, not the P prime. The P prime, they are the member end force components in local coordinate system, but we like to get these. And how can we get the P? We need to multiply R transpose to the P prime. Okay, so we can multiply the R transpose to the P prime, which can give you the P, And the R transpose to the P prime will be the R transpose K prime R times E. Okay, so that's the result we like to get. Okay, and remember we need to calculate all these three. That's the so if we like to get if we calculate these three, it will be the K. Okay, so that's the calculations we need to do. If we like to if we got the K prime matrix, then if we like to get the element stimulus matrix in K matrix, then we need to multiply these three together. To to get the K matrix. Okay. So that's the for the element stiffness matrix. Okay. And remember when we consider the inclined roller support problem. Okay, wait a minute for 1 second. Okay. Okay, we have another problems. It is the homework problems. If we got the inclined roller supports, we can do two things. We can use two different methods to solve these problems. If there are the nodal points node 1, 2, 3, and at the node 3 we got an inclined roller support, and we can follow the usual solution steps for the common solution procedure. We will transform the element stiffness matrix to the global component first, and then we can assemble the element stiffness matrix into the global stiffness matrix. That's the K matrix. That's the K matrix. And for the common solution steps, we will use the global components to consider the contributions from different elements. Okay, so that's the usual solution procedure. We can get Ku equal to the P. And in these expressions, first it is the global K matrix, the global U vector, the global P vector, and also in these three matrices I didn't add the prime. So it means all the components, they are in the global components. But if we use the global U and the global V for the node point 3, and for these problems, we can define the X double prime and the Y double prime. Okay, even I added the 2 double prime, the X double prime and the Y double prime, they are also the local coordinate system, since the global coordinate system is always there is only one. As long as I use the X and the Y, it is always means that they are the global coordinate system. But if I use the X prime and the Y prime, they are the local coordinate systems for each element. Right now I use the X double prime, the Y double prime. So it means the vector components, they are the okay. But for these problems, for the U3 double prime, it is not equal to 0. But the V3 double prime, which is equal to 0. Okay, since in these expressions we know the restrained directions, which is along the y double prime direction. And right now I got an inclined roller. The restrained directions, which follows the y double prime directions. For these node points, we know the U3 double prime. It must be equal to 0, but the U3 double prime is not equal to 0, since the roller supports allow the movement along the perpendicular direction, so that's the x double prime direction. But if we use the global components, U3 is not equal to 0, V3 also not equal to 0. So we cannot use the traditional treatment for the rigid support. For the rigid support, we can use the MIT's method. We can use the Berkeley's method. For example, if we use the Berkeley's method, we just add a very large number. I call this number as the K bar. We can add a very large number to the diagonal element. Then we can restrain the results of this element, which must be equal to 0. Okay, but the restrained components must be one of the chosen components. But if we use the global components, both U3 and V3, both of them, they are not equal to 0. But the soft U3 and the V3, the resultant movement should be along the x double prime direction. But both U3 and the V3, they are not equal to 0. Okay, so right now I like to transform the U1, V1, U2, V2, U3, V3. Okay, that's the original vector components in this U. But later I like to transform it to the U1, V1, U2, V2, and the U3 double prime, V3 double prime. Okay, so that's the vector transformations. Originally we got the global components, but later only for the node pointer 3, we like to transform the vector components from the xy components to the x double prime, y double prime component. So that's the original one. That's the target one. Okay, we like to transform the U3 and the V3 to the U3 double prime, V3 double prime. And also the P vector. Originally we got the PX3, PY3. Both of them, they are along the global X and the global Y. But later I like to transform the vector component P for the PX double prime 3 and the PY double prime 3. Okay, the fourth components also I like to transform to it. And for this one, usually I need to use an R transpose. Okay, remember, whenever we like to transform the vector components from the global to the local, we need to use an R transpose. So the R transpose so that's the R transpose. Since we don't need to transform the vector components for the first two node points, so we just use unit vector, the element 1, which must be used for all the diagonal elements. But for the U3 and the V3, originally they are the components in global coordinates. Later, we like to transform it to the U3 double prime, the V3 double prime. So that's the R transpose. Remember, the negative sign will be on this one. And the P vector, or the P double prime vector, which is equal to the R times the P, which is equal to the R times P. Okay, so if we got the vector components in global coordinates, then we can pre-multiply the R matrix to give you the P double prime. And it will be the R times global K R transpose U double prime. Okay, so for the if we like to transform the vector components from the global to the another local components X double prime. So for this one, for these problems, you need to calculate the R, K, R transpose. The negative sine theta will be the post-multiplied matrix. R transpose will be the post-multiplied matrix. And the R matrix will be the pre-multiplied matrix. Okay, so I think for the previous derivations, sometimes I mix but you need to check which one you like to get. If the new one is the vector components in the local, then you need to calculate the R transpose U double prime to give you the original U vector. And we like to get the P double prime. The P double prime, we use the vector components in X double prime and Y double prime. So we need to pre-multiply the R matrix. Okay, so for different case, we sometimes the R transpose will be the pre-multiplied matrix. Sometimes the R transpose will be the post-multiplied matrix. We need to see which one we like to get, which one is the original one. Okay, so that's the first hour's class.